One Africa TV's #LearnOn1 and Hollard Life are teaming up to give lucky teachers an awesome goodie hamper. All you have to do is tell us if you'll recommend #LearnOn1's free, quality, supplementary lessons to your students. Simply SMS a yes or a no, including your name, the town you live in, and the school you teach at. It's that easy. Invite learning in today with #LearnOn1 and Hollard Life. Competition closes on 16 October 2020. Standard T's and C's and SMS rates apply. For more information, visit learnon1.org.
Grade 12s, good morning. We are going to start with the section on radioactivity. Now, at the end of grade 11, we did the chapter, we started with cathode rays. Okay, and radioactivity follows on in that chapter, so it's page 352. Just to recap, because they sort of fit together. When we did cathode rays, we said, what are these cathode rays? Remember, we had to heat up a filament with a high potential difference across it, and it would give off electrons. We said they are fast-moving particles. They have a negative charge, fast-moving electrons. They have momentum. Can you remember the Crookes paddle that could start rolling when the electrons went smashing into them? All right, so they've got momentum. They can be deflected in a magnetic field, and it will be according to the right-hand motor rule with electron current. No? And then it's also deflected in an electric field, and you will find that it is always deflected away from the negative towards the positive, which is an indication that it is a negatively charged particle. All right, so probably then an electron, yeah. I think it will be probably a little bit slower. Okay. The Cathode Ray Oscilloscope, I don't want to say much about it. We had a look at the cathode ray and the deflection between the X and the Y plates. We can use an oscilloscope to measure potential difference of a source. We've done that. Previous period, we've had a look at the photoelectric effect and the quantum theory. I don't want to say much more about that, but these parts all connect up with this next section, and that is radioactivity. Now, when I talk about radioactivity, I think most of you have got a little bit of an idea, oh, it's dangerous, or be careful, or causes cancer. I think there will be various thoughts in your head about it. All right, so what exactly is radioactivity? We say that certain elements, not all of them, certain elements are so-called radioactive. What does this mean? Well, very simply, in the first place, it has an unstable nuclei. The idea of radioactivity is a form of energy that is being given off. If something gives off energy, it tries to go to a lower energy state, which would be more stable than a higher energy state. So it is an unstable nucleus. Just sort of important, radioactivity is a form of energy that comes from the nucleus of an element. All right? So we refer to the nucleus as being unstable. The nucleus gives off energy in the form of something called radiation, and radiation is a collective word. We'll come back to that in a moment. All right. Unstable nuclei can sometimes break down. They literally shoot out a particle. All right. And then it gives off radiation, and it can form a new element. I don't know if you've ever read up about the old alchemists. They tried to change lead into gold. All right. They were never successful. But for example, uranium, which is radioactive, it gives off energy, and it keeps giving off energy or radiation until eventually it ends up as a very stable element, lead. All right. So, sometimes, not always, we find that pieces of the nucleus break off, and we will end up with a new element. This change from one element to another is known as radioactive decay. All right, the decay process. A radioactive source, when it's brought near to an electroscope, will charge up an electroscope. The reason for this is when we have radiation and it travels through the air, it knocks off electrons from air particles, and it causes the air to become charged. It ionizes the air. All right. So sometimes we refer to the radiation as ionizing radiation. All right. Ionization implies electrons are knocked off the air particles. What are air particles? Oxygen, carbon dioxide, water vapor, nitrogen in the air. Okay. Now, the radiation that is given off by radioactive isotopes are dangerous. Your body, as you are sitting here, is receiving some radiation. Okay, your body is designed to cope with some radiation. In actual fact, it is some of this radiation that keeps your skin sterile. I don't know if you've ever noticed in the winter if it's very cold, especially if you're in a damp climate and you keep wearing jerseys, you sometimes get itchy spots on your arms. Don't know if you've ever noticed it. That's fungus growing. Okay? The sunlight, the radiation, keeps your skin sterile. Okay? It kills off bacteria among other things. So, then you wash off all the dead skins. Okay, people, radiation is dangerous. The first scientists that worked with radiation, I'm referring to Madame Curie, and she and her husband, they all died of leukemia as a direct result of the radiation they received while they were working with it, because they did not realize that it was so dangerous. Okay. We get 3 types of radiation. We talk about alpha radiation or alpha particles. All right, very important, it's a particle. Beta radiation is a beta particle. Okay, so it's literally a particle, like a grain of sand is a particle. The last one, gamma radiation. Where have we done gamma radiation? Yes, it's part of the electromagnetic spectrum. It's a very high frequency wave. Transverse wave travels at 3 times 10 to the power 8 meters per second through a vacuum. All right. So radiation is not a particle. Gamma radiation, people, is an electromagnetic wave. And it obeys all the wave properties. V equals F times lambda. It can be reflected, refracted, diffracted, interfered, etc. Okay. Now, we are going to have a look at these 3 types of radiation and what exactly it entails. Starting off then with alpha particles. The symbol for alpha is the infinity symbol. Okay, it's the Greek letter. Alpha particles. Now, an alpha particle is a little piece that breaks off from the nucleus, and it consists of 2 protons and 2 neutrons. So the mass of that particle would be 4 atomic mass units. All right? Now, 2 protons and 2 neutrons is actually a helium nucleus. So we refer to an alpha particle as being a helium nucleus. It would be a helium nucleus. How many electrons would helium have? 2, without the electrons. All right. So 2 protons, 2 neutrons. Because it's a fairly large particle, it consists of 4 particles in the nucleus. All right? 4 nuclear particles, relatively speaking big. If you think of hydrogen, an atom of hydrogen has 1 proton. A helium nucleus is going to be 4 times bigger because it's got 2 protons and 2 neutrons. So it's a relatively big particle. When it travels through the air, because it's a big particle, it can easily knock off electrons from air particles. So alpha particles cause a very large amount of ionization of the air. One problem with alpha particles, or maybe not a problem, but it cannot really travel very far through the air. It can travel about 1 centimeter. So at this point, if there was alpha radiation in the air, would it affect your body as such radically? No, maybe if you swallowed it or breathed it in. Okay, but it's stopped by a couple of centimeters. So if this was an alpha emitter, would Luan have to worry about it? No, it can only travel about 1 centimeter in air. Because it's a fairly large particle, it's easily stopped. What charge would a helium nucleus have? Rarig. Wil jy vir hulle sê hoekom? Yes, people. A helium nucleus consists of 2 protons. What is the charge on a proton? Positive. And 2 neutrons. What's the charge on a neutron? Nothing. So we have 2 positives and 2 neutrals. What charge do I have? Plus 2. Okay, I have a positive particle. Now, in a magnetic field, if I had electron current, that particle would be deflected according to the right-hand motor rule. Are you with me? Now, I have a positive particle, so it's going to be deflected in the opposite direction. So we can say then, alpha particles will definitely be deflected in a magnetic field. And if you work with the right-hand motor rule for electrons, it's going to go in the opposite direction because electrons are negative. It will go to the opposite side because it's a positive particle. So it's going to be deflected opposite to the direction that a negative particle would be. You can either think of it that way, or you must use the left-hand motor rule to tell you in which direction a positive particle will go. Remember, conventional current goes from positive through the circuit to negative, so it's actually a positive particle that is moving. Do you follow me? Okay. The next property, it will slightly be deflected in an electric field. And it will be deflected away from the positive plate. Now, it will only be deflected slightly in terms of a single electron being deflected. An electron is a very light particle. It will experience more deflection. So a heavy positive particle, it will be deflected, but not radically. Okay, so it's slightly deflected, it's slightly deflected slightly, okay. It's just deflected slightly in an electric field, and the direction would be away from the positive plate. Why? Like charges repel. A helium nucleus has a positive charge. It's going to be repelled from the positive plate towards the negative. Alpha particles can only move a centimeter or so through air, and it's very easily stopped by thin sheets of paper. It cannot penetrate a sheet of paper. All right. So if you are wearing a shirt or even your skin, it can't really penetrate that. It does not have a high penetrating ability because it's a relatively large particle. A smaller particle would have a higher penetrating ability. When alpha decay happens, right, we have over here a uranium nucleus. It's in your books. All right, we have uranium. atomic number 92, and they work with isotope 238, that's the radioactive one. It is going to undergo alpha decay, which means it is going to shoot out a helium nucleus. Okay? Going right back to conservation of energy, can I create or destroy energy? No, so I can't really create or destroy matter either. I can't make it out of nothing. So, at the end of this reaction, if I have thrown away 2 protons and 2 neutrons, what will I be left with? I'll be left with 90 protons. I started out with 92. So it'll break up. I'll have 90 there and I'll have 2 there. What mass number would I have? Yes, -4, so I would have 230 over there. Now element number 90 is thorium. Zeg weer? Oh, 234, excuse, right, there. Do you follow me? If I go and add that, I should get that. And if I go and add that, I should get that. I still have what I started out with. Alright. Although I no longer have uranium, I now have an element thorium. And because thorium is the first product in the radioactive decay from uranium, I will call thorium a daughter isotope of uranium. Yes. They're both metals. Thorium is also radioactive. It will undergo further alpha decay. It keeps doing this till you end up with lead. Okay. I can't use thorium, for example, in a nuclear reactor. No. Okay. No. No, no, not at all. No. It'll have a different melting and boiling point. It will have slightly different densities, conductivities, etc. Okay, it's a unique element on its own. Well, some elements, for example, those in group 1 have similar properties. Similarly, the lanthanides and the actinides would have specific similar properties. Okay, but thorium is also radioactive, but it is not, except for the fact that it is a daughter isotope, it is not uranium. All right. Okay, that is alpha particles. Very important to remember. A helium nucleus is an alpha particle. Consists of 2 protons and 2 neutrons. It's fairly heavy, so it does not have a very high penetrating ability, and it's very easy to stop it. It can't go through paper. Now, the next one is, I've got the whole range. Uranium goes to thorium, and then thorium has a daughter isotope, radon, and is it radon? No, it's not radon, it is radium, and then radon, and then polonium, and then lead, and lead is stable. Lead won't break down any further. So the decay of uranium, in a uranium mine, you will very definitely get some lead as a byproduct, and even some of the other elements, although they are sometimes just not very stable. And there aren't many uses for them, so they won't necessarily try and extract them. Radon, this one, is it a, yes, radon is a gas. All right. The next form of radioactive emission is the so-called beta particles. Now, a beta particle is a fast-moving electron from the nucleus. Now, remember I said to you just a few moments ago, radiation is energy that comes from the nucleus of an atom. Now, the structure of the atom, we have protons and neutrons in the nucleus, electrons around the nucleus. So where does this electron come from? Now, this electron over here, it comes out of the nucleus. But what happens is a proton breaks up and it forms a neutron and an electron. And it's this electron that is shot out. Okay, that electron is the so-called beta particle. All right? Yes, it stays in the nucleus. All right, now, here I've got an equation. I've got carbon-14. Now, carbon-14 is a beta emitter, which means it's going to shoot out an electron from the nucleus. But now remember, if we go and look at the equation on the left-hand side and on the right-hand side, the stuff that I start out with, I must end up with, in total, the basics. So here, I have got 6 carbon atoms. Over there, I've got 8 neutrons. That's why the mass number is 14, of which 1 proton is now going to break up, and it's going to form a neutron and an electron. So, my atomic number must increase with 1 because I gain a proton, don't I? Well, I don't gain it, but I get a proton in the nucleus. Because, a neutron, I get a neutron. No, it's the other way around. A neutron breaks up into a neutron breaks up. A neutron breaks up, into a proton and an electron. Sorry. Okay. Yes, it's wrong. The neutron must break up, forming a proton and an electron, which means I will gain a proton. The atomic number will increase with 1. Now? Okay. The atomic number will increase with 1. What's going to happen to the mass number? It's going to stay the same. Why? Yes. So what do we know about the mass of an electron? It is so tiny we ignore the mass of an electron. Now you can go and work it out. It is 1,840th or something of that of a proton. But it is so small it's negligible. We ignore the mass of the electron. So the total mass will remain the same. Alright, so we find over here that the mass number remains 14. Here is the electron that is released from the nucleus. An electron has a charge of -1. So if we go and have a look over here at the overall charges, 6, we end up with 7 there, -1 is 6. Okay? The overall charge. The mass number, because an electron doesn't have a mass, the mass will stay 14. In other words, the number in total of protons and neutrons is still 14, although 1 neutron has changed into a proton and an electron that has been released. Now, this electron, it's a relatively small or large particle. Small. It's very small. It's so small, it almost has no mass. The mass is so little, we ignore the mass. So, beta radiation can travel much further through air. It can travel many centimeters through air. Because it's a very tiny particle, for 2 tiny particles to collide, the chances of that is smaller. So it will cause less ionization. So if I have 2 unknown sources and I can measure the amount of ionization, if there is more ionization, I could maybe say it's possibly alpha radiation. If there was less ionization, there would possibly be beta radiation. There are other things we look at as well. Okay. It will deflect in a magnetic field and it will deflect in an electric field. Charged particles are deflected by magnetic and electric fields. If we look at the deflection in the electric field, we find that this particle is going to be repelled from the negative pole and it's going to go towards the positive electrode or plate. So, it will be deflected in an electric field away from the negative. In a magnetic field, it's simply going to be deflected according to the right-hand motor rule, because the right-hand motor rule is for electron current. And then we will say, well, the deflection of the electron is at right angles to the direction of movement and the magnetic field. All right. The deflection will be more than that of an alpha particle. Why? Is it heavier or lighter? Lighter. Is it easier to push a heavy object or a light object? Of course, a lighter. So the electron, the beta particle, will be deflected a greater amount than the alpha particle. We can reduce the amount of beta particles by very thin sheets of aluminium, for example, aluminium foil. It will be stopped by approximately 5 millimeter sheets of aluminium or thin lead sheets. Why lead? Lead is very dense. Okay, so the nuclei are closer together in the crystal lattice, so it's harder for something to get through it. That is why they use lead to stop the radiation. All right, it's fairly cheap and it's freely available, etc. Okay, that is beta radiation or beta particles. I'm going to stop with gamma. We've done gamma. Gamma radiation is not a particle. What is gamma radiation? An electromagnetic wave, one having very high frequency. Energy is directly proportional to the frequency. Okay? It will cause very little ionization. Why? It's not a particle, so it can't so easily knock off an electron. Okay? It will not be deflected by an electric or magnetic field. Why not? It's not charged, so it can't be deflected. It can travel up to several meters through air because it's not a particle. Okay? It can travel quite far. It will have a very high penetrating ability. We would be able to absorb it using very thick sheets of lead, but it can very easily penetrate paper and aluminium. It will be absorbed, but not perfectly stopped with thick sheets of lead. So if they want to stop gamma radiation, the Large Hadron Collider in Switzerland in Bern, do you know where it's situated? Where? Well, where? On top of the ground? In a skyscraper? Deep below the ground, built into a chamber, and there will be thick concrete walls and thick layers of lead in the wall to prevent gamma radiation from entering. Okay, very difficult to stop it. Alpha and beta emitters. Certain elements are alpha emitters, certain elements are beta emitters. It just depends. For example, the uranium was an alpha emitter. Carbon-14 is a beta emitter. But whether it's an alpha or a beta emitter, the moment it shoots out a particle, there's a hole in the nucleus. So the protons and neutrons that are left have to rearrange to fill up that hole. The moment they do that, they give off a burst of gamma radiation. All right. So any alpha or beta emitter will give off gamma radiation, and then we find that some other elements, without being alpha or beta emitters, will give off gamma radiation. All right. We will stop.
This lesson is proudly sponsored by the Capricorn Group.
Access to all your favorite local and international shows wherever you go? Here's how. Head to showmax.com and click try for free for 14 days. Enter your email and create password. Choose your plan and payment method that suits you and start watching